There are three missing ingredients for testing these quadruplets. First, where are the muons? Well, very conveniently, our Earth is being bombarded all the time with particles from space. When they interact with our atmosphere, that creates a cascade of mostly muons. So that's what we use to test these quadruplets with.
So the second ingredient that we need in order to make these detectors work is high voltage, right? And that's supplied by this guy here. It's called a Kane module, and it's a common tool used in particle and nuclear physics. So it's just connected to a wall outlet, and electronic components help output the high voltage we need, which is usually around 2900 volts to 3000 volts.
Third, and this is a little trickier, we need something that tells us when to record from the quadruplet. We do that using scintillators. Scintillators are an old and robust type of particle detector. The top and the bottom of our test bench are layers of scintillator. When a muon passes through the test bench, it will trigger a scintillator in the top and a scintillator in the bottom. The signal from the scintillator goes to the NIM crates where it's processed.
What Leah said, so these are the devices that we use to process those signals from scintillators. They're known as NIM modules, and they're commonly used in both particle and nuclear physics. The final decision on whether to read out our STGC electronics comes out through this cable here. So if you follow along, I'll show you where that cable leads to. Yeah, so it's a pretty long cable, and it goes all the way from our NIM modules to here. So this is connected to our readout electronics. So when we have a trigger signal coming out through here, it triggers a readout of everything that we collect from the front end boards connected to our module here.
With the pentane bubbling and the scintillators on and the high voltage on, we're ready to collect cosmic muons. We do that by just leaving all the equipment running for about 4 hours, and in those 4 hours we collect about 2 million muon events. Now we'll show you what a muon signal actually looks like.
All right, so we have high voltage going through the quad right now, and our front end board is connected to the quad and obviously powered. And what we have is this little EMO cable connected to one of the outputs to the front end board. So if we follow this this cable here from the front end board all the way along our test bench, you'll see that it's connected to an oscilloscope. And what we have on the oscilloscope screen right now is a typical signal that we read out from these front end boards. So that's actually a pad signal, which we talked about earlier. We get signals from all the electrodes from a quad and all the layers, and that helps us reconstruct muon tracks. So if we're lucky enough here, we might see another pad signal just like that. This one's obviously a little bit less prominent, a little less strong, and that's very typical in experimental physics. You'll have a vast array of different signal strengths as we start collecting data here. So maybe we can try one more. All right, so sometimes we'll see some noise as well. That's very typical in physics. There, okay, here's a big guy that is so big that it got cut off by the screen, but again, that's a very distinct muon passing through